Hello, everyone. Thank you very much for this last talk. Our next speaker is a principal developer of the JOC programming language for SORP and Nock-chain. Sorry if I mispronounced that. Please welcome Neil Davis.
Thank you. You are correct. Zorp and Nock-chain is the project there. I am working on a scripting language that compiles to Nock. You heard about Nock a little bit earlier today when Curtis Yarvin spoke about the Urbit platform, and there have been some other talks. Carol Affanen spoke about Urwasm, which runs on that platform as well. Okay, so what you would hope to get out of this talk today, that may be up to you, but what I hope to convey is an appreciation of the way in which the Hoon programming language in Urbit uses its type management system, in a sense, of what we're going to call a vase, and we'll come back to a little bit to the terminology later on, to manage the production of untyped code. Now, I am going to incidentally use some Hoon, and you will incidentally see some Nock code. I'm not actually going to show you the Nock specification. You don't need to know Hoon or Nock code to follow hopefully anything that I'm saying today, if I do this correctly. It would probably enrich your experience with what is going on, but you don't need it to do this. So we're going to be talking in kind of an abstract level about what do you do when you have a compile target for your instruction set architecture, for your VM, for whatever you're producing. Some of these things would carry over to principles of assembly languages and so forth. When that compile target doesn't have type, and so you have to decide how you are going to manage and enforce the restrictions that you would like in a human legible language, either statically or dynamically, such that they carry down to what's being produced without losing the information that you would like. For instance, as a trivial example of this, you may write a programming language that is using certain values as constants. And you would like to permit in something like an enum or a struct kind of scenario, only certain values of these constants are permitted. At the untyped level, there's essentially nothing that might tell you whether or not the value that you're looking at is just like a raw set of bits on the computer should be thought of or treated as a constant. But you have to carry around somewhere some metadata that lets you identify whether or not this is a constant, and therefore whether or not you would allow it to be mutated or altered in some way, or whether or not it is fixed and treated as this static persistent value. Other places that we use this notion of type that we'll get to here will be in dealing with live code evaluation, in which we've received something as text or as some other kind of code artifact, something like maybe like a quoted Lisp expression. And now we need to run an eval. We need to evaluate this expression. We need to say what it does. Maybe we want to sandbox this. Maybe we're running it raw directly on top of our machine layer. We may want to do something like metacircular interpretation. So what this would be is where we are virtualizing our code. So we're going to be running something like Nock code in this case, although it would carry to other ISAs as well. You're going to run Nock code, and one of the interesting things about Nock is that it's a crash-only language. So if you're running raw Nock on a raw system, like you have a Python interpreter, you have you're running it on the Ares platform for Nock app, which is Zorp's product. You're running it on Vare, which is the Urbit virtual machine layer. You're running it on there. You hit an invalid expression that reduces to something that cannot be evaluated, it will crash. Now, clearly, in a production system, this is not a desirable property. You'd like to be able to do something about this. The way that Nock manages this typically, the way that an interpreter for Nock manages this is that it virtualizes the code, which means you can introspect into the code artifact and you can ask questions like, does a value corresponding to this exist? You've asked it for the name of some function that you'd like to evaluate. If this doesn't exist, then your code would crash in some sense. You do not wish it to crash. Therefore, you would like to be able to ask questions about it, like in the type of this code, the subject type of this code, the values that I know, the things I know about this code, does this value exist? And therefore, am I able to make decisions about whether or not I would run it through or what would happen when I did that? So we're going to be able to do this at a lot of different layers using what Hoon calls a vase representation. At the object level of what a vase is, it is a type-value pair. And so what this means is that Nock being untyped, the only values, and homoiconic, which in this case means that the executable code and the data representation of data and code are the same. There's not two different, like if you look at like an assembler language, you're going to have things that are commands, you're going to have things that are memory addresses, pointers, you're going to have things that are raw numeric values, you're going to have large blocks that are binary blobs that get treated in various ways. In some sense, assembler is untyped, but in another sense, it's positionally typed, right? Like the position in an instruction dictates the way that it gets interpreted by the CPU. So there's kind of a what you might think of as like a poor man's type system. There's been some interesting research work done into typed assembly languages as well that have some commonalities with what we're talking about here, but okay, so circling back around. What we mean when we talk about type is that when we have a raw value in Nock, and this thing is simply a non-negative integer. So you have the non-negative integer 32 in decimal. And you're going to say, what does this mean, right? What does it mean when we actually have a 32 decimal value? Or, OX20 in hex. And this depends on the metadata that we attach to it that allows us to interpret what's going on. So if we interpret it as an ASCII character, this is going to give us a space. If we interpret it as a memory address, this is going to give us some kind of value. And so a vase is this pairing of, we're going to say the head, the leader of the tree is the type, and the tail of it is the value. The value can be a raw number, it can be a cascading binary tree of values. They will terminate in, the leaves of this tree will terminate in values because we don't permit anything to be a cyclic graph, so that it's always terminating, it will always terminate in non-negative integers, but you can have these as pairs in a binary tree. And so everything in Nock is a tree. All right, and so my talk nominally is vase mode. This is going to give us an idea of how do we actually work with such pairs essentially at the meta level rather than at the object level. The other thing that this is going to let us do, and this is the primary way in which it gets used in the compiler. So you get the metacircular interpretation, you get some of these other properties. It is going to let us do live code eval in such a way that we can use a statically typed language, treat the values dynamically while we're working with them in the compiler or inside of the eval, and then produce the untyped, raw, executable Nock code at the termination of that process. So in essence, you can think of this as a way of lifting a value from a statically typed context into a dynamically typed context. Vase mode operations are when you're performing everything on that dynamically typed sort of temporary construct, and then producing a final code artifact coming out of this. All right. The white paper from 2016 actually makes a very scant mention of vase mode. And it's primarily focused on one of the nice properties, which is because we can reload vanes from source, a vane being essentially a kernel module in Urbit. We can hot swap code because we can compile it using an eval, and then we can update the state of the system in the event log to point to this new noun that we created, and we can now execute this code that we did as a result of that. Now, when we talk about type, I say this is a type value pair. We're using type in a sense more like Haskell, where what we're talking about in a type is name bindings, aliases, docstrings, so in code documentation that's generated from comments adjacent to the code, so you can introspect, you can ask questions about it. And so this means that we can carry around this information in the compiler, evaluate against it, and then produce a code artifact. I'm going to give you 3 pieces of code here. The top of this is actually the public debut of Jock as a language, right here. This code works. I'm calling it the alpha here because the alpha of the language is in development. It's what I work on normally. It's designed to be Swift-like. I'm including it in here because it's nice pseudocode, because it's pseudocode that you can actually type in and run in a certain place, which has a nice property to it. The Hoon equivalent here is pinning a value with the label A and then returning that value. And then the Nock equivalent, if you're interested in the mechanics of Nock, I'm doing a workshop tomorrow afternoon that will actually walk you through how would you construct a language using an SKI style combinator calculus. How would you actually produce a code using that? But here what this means is that an 8 means a composition of a constant value, which is a 5, and we are grabbing the head, the rightward branch, the leftward branch. I am doing my stage operations here. We're grabbing the leftward branch of the composed operation here, which means grab that 5 and produce that 5. All three of these are the same. If I evaluate either of the top two, it will produce the Nock code on the bottom. So that's the operation here. Now, if I step, and actually, I'm also in this talk going to give you a slightly non-canonical pseudocode interpretation of Nock in a few places as a mnemonic for you here. I'm going to pull up a REPL in a moment, and we're actually going to look at some values and see how to build a vase, and then how to manipulate vases, and we'll go through some of these things. But here, if I type in, if I produce a vase of the value 5, what Urbit tells me is that it's a cell, so it's a pair of two things. One of them is this weird hash t / at ud, and one of them is a 5. And so you can infer, given the subject of the talk and what I already mentioned, that this is a this is a type value pair. And if we actually, this is because the pretty printer in Hoon is very aggressive about collapsing types, because types can be quite large. And so it means that if in certain instances, we're actually going to have to step in and kind of manually extract these pieces if we want to see what's going on. I will be doing this. Incidentally, again, watch the products of what I do, not the code that I'm writing to produce it, if you want to stay focused on that. So here it tells me that it is an atom, which means a non-negative integer. It has a bit of associated type, which in this case means an unsigned decimal. And then there's a sig there, which in Urbit is the placeholder for 0 or empty value, which in this case means that it's not constant. If it were a constant value, then there would be something else there, and we would use that as a marker to tell the difference between a constant and not. In either case, the value would not change. Right? So if I were to interpret this as text, if I were to interpret this as hexadecimal memory address, in like an IPv4 web address, whatever, this metadata would change. The value would not change. It's just that the type and the thing that we're doing to interpret it would change. So this is an example here of doing it with a cell. And so, similar code breakdown. You can see here we have an extension of putting a constant 5, a constant 10, grabbing that pair out. So here, what it looks like in the type of type, in the type value here is we have a cell at the head of our description, and then a piecewise description of what's going on there. Now, I made a reference a moment ago to trees, and Nock, everything that is non-trivially an atom is a binary tree. You'll notice that in one sense, this has the same structure as a binary tree, because we have a label, and then it's referring to two children of this label at the head of this binary tree. If we were to actually diagram this out, it would sort of loosely correspond to that pair over there, which is just, it's an upside down V. It's a binary tree with only two values. But there's some disambiguation that we have to do in the compiler if we actually want to trace down and grab the right thing as we do it. So there's some tooling for this. All right. Let me switch over to all right. This is doing some strange things with my layout, but I think it should be Oh, it's not great, but it might. You know what? Let me unmaximize it. No, not doing. Problem is I'm mirroring a terminal session, so I can do it on 2 screens, and it's not sure if it wants to cooperate with that. That is probably close enough to make it work. Okay, well, I told you not to pay attention to the code that I'm typing anyway. That's not going to be a problem because you can't see it all. All right, that's fine. All right, so if I ask it for the type of this vase, I wish the spaces were showing up there. That would be a little bit more legible, but it's okay. So I'm getting my head and tail of those 2 values and producing those. Okay. So if we were to do it to a hexadecimal 5, oh good grief, I think I am going to have to reshape this just a little. Let me actually try. Oh, there we go. Okay, Zoom fixed it. All right, that'll work there. Okay, so there's a quick example where I give it a 5 as a native unsigned decimal. I give it as an unsigned hexadecimal, an unsigned hex value. You can see it changes the metadata that it's carrying around with it. And the pretty printer does this magic, does other things with it. Okay, now, because Nock only knows about nouns, all that type information is living in the head, the type characteristic as I suggested. And let's go to, yeah, okay, we'll come to that in a second. All right, so what this means is that I can use a vase of my type and my value, work with these things, as we'll see in a moment, and then turn them into raw code. It also means that there's an interesting thing that can happen because I can manipulate this value, this type, independently of the tail of the cell. And so I can build this custom. It's sort of like actually producing an abstract syntax tree of your code, an AST. You can generate it, build it using other means. You can edit it. You can send it to someone as this broken apart vase, this type and this value, and ask them to reconstruct it on their side using what they have. This is the way that system upgrades in Urbit are set. For instance, you're sending this information over the wire, and then people are reconstructing. They're doing their own eval of what they receive on their end, which is, in some sense, it's kind of a code security mechanism to have this available. Now, this information on the left being carried separately from the information on the right means that we can actually do some strange things like create an artificial vase. Let me see. Calling it a vase. I'm going to call it a hexadecimal value, and I'm going to do something questionable, which is pass it 2 different values. So here I've passed it a cell, a pair of a 5 and a 10. Is this now accurate based on what we just saw earlier? So what we saw a moment ago in the other example was if I ask it for a vase of a pair of values, this is a cell. So here I've created a vase manually, structurally, in which the value does not correspond to the type that I'm claiming for it. This is bad. We never want to do this, which is one reason that we don't typically, sometimes we manipulate these directly, but we don't want to do this. This is what we would call an evil vase, and we don't want to actually run into these while we're doing this. All right, let's see. All right, now that we have some tools, now that we have a little bit of feel for what a vase is, we can talk about some of the tools that you use to manipulate them that allow you to actually produce code that you can then execute and work in different ways. So we can in-vase code one way. We're going to use that I call it a ZapGar rune. You don't need to know the ZapGar. You need to know that you can in-vase code. You can turn code into it. You can turn a value into a vase. You can devase code, and the thing that you notice when you devase code is that on the, so I hope I do have a mouse here, okay. So over here I've made a vase of a value, so this is a vase. When I devase it, I also have to make an assertion about the target that I'm aiming for, and this is where the evil vase comes into play, or if I'm trying to devase something and it has a different value, a value that it cannot correspond to the description of the type that I have, it will break here in interesting ways. Anyway, so you need to devase, you need the information about what you intend to receive as well. It's not simply apply the type that it's claiming to the value. It's saying apply the type that it's claiming to the value and assert that it matches the type that I expect coming out of this, which is additionally a safety mechanism, because what you're doing when you apply the type to a value is you're basically running raw eval, right? Like raw live eval on what's going on. Now, let's go back over to our interpreter here, our command line. All right, we have those. Okay. Let me run through a couple of live examples here. Okay. Now we need to say what kind of thing, how do I want to say this? We need to be able to produce code that can be evaluated against the values that we have in a particular vase. Generally speaking, we're going to use vase as eval, or we're going to use it inside of our metacircular interpreter, or we're going to use it to hot swap code. But what we're really concerned with is evaluating, we're either concerned with evaluating the thing that we have in the vase. More commonly, we're concerned with evaluating some other bit of code against what you have in the vase. One way to think of this, probably the cleanest way to think of this is, here we go. Okay, so this is a sort of an analogous Lisp process here, but this will highlight one of the differences that goes on. So here we've defined a program and we've used the quote operator in Lisp. When you quote something in Lisp, it essentially defers the evaluation. If I did not have that quote and I ran the operation +1, 2, it would simply immediately resolve to 3. Right? The code is live, it just goes to the next step. When you quote code in Lisp, what it does is it keeps it basically as a structural AST. And when you have this structural AST, now you have code that you can introspect, you can ask questions about, you can manipulate. So if I ask it for the head here, or the addition, so the tail, the head, then I get the plus. If I ask it for the tail, it gives me the pair 1, 2. And Lisp is a little different because this is an S expression. It's more like a list than like Nock's binary trees, but it's very closely analogous here. If I evaluate that code, if I ask it to unquote that code, then I'm turning it from the representation that it has here back into a piece of live code, and I'm running that code. The difference that we're going to see against what Hoon does and Urbit does is when we run that code in Urbit, we are going to explicitly supply this vase that the code will be evaluated against. We're going to eval code against a given vase. We're going to provide it that information. Lisp here is using the current global subject. So when you do eval in Lisp, you either have to construct an explicit subject or you're evaling it against the global subject. It's extremely hard to make completely general statements about Lisp, given the schisms that have taken place over time, but I think that's a fair way of representing what Lisp gets you there. All right. Now, okay, so what we're going to be interested in here is taking something like an AST, okay, I'm running a function ream against text 5. and I'm getting this AST back. This is not a vase. This is not a type. Okay, we're going to set the vase aside for a moment. We're going to come back to it in 2 minutes. This is an AST that describes a non-constant unsigned decimal with the value 5. It has some similarities to what you saw earlier. It's not the same thing. It will produce the same thing when we evaluate it, but ream is basically the function in Hoon. We're infamous for Bohemian terminology in our names here, but we're going to ream. Means that we've supplied a piece of code as text artifact that we are going to turn into an AST. When we have this AST, we are going to evaluate it against a given vase, a vase that contains information about what's going on. So in this case, what I would be able to do is I would be able to say something like, given a vase of a declaration like a equals 5. Well, let me do this in 2 steps. Okay. When I create a vase of a equals 5, there's a subtle difference here, which is that we're carrying a name around. Right now we have a variable name that's attached to this, and so if I'm going to do something like evaluate 5 against it, what this means now is I can produce a code artifact which is A. In this case, it means a wing is a search path into your tree. It's saying find the A, and we're going to run that A. So if I were to just run that A live, it would tell me that there is no A. I have no A. So this is equivalent to running the Lisp a minute ago of just eval my expression, which would eval against my current global scope. Here, if I do that, of course, nothing happens. What I'm doing inside of the compiler looks more like this. I'm going to slam. Yes, slap, you're right. Well, slap puts them to, yes, you're right there, yeah. The downside of somewhat Bohemian names is sometimes your mnemonics fail you when you're running something live. Okay, so here what we've done is we've created a Hoon AST, and we've created a vase that contains the information necessary to evaluate that Hoon AST, and we ran it against that particular vase. So one of the most common operations that we're going to use with vases is we are going to simply run code, run an AST against a vase. We're going to use it as our live eval. We're going to use it to get answers out of what's going on. This has some interesting consequences. So for instance, if I were to say add A2, why does it blow up here? Assuming that this is valid code, add A2, which it is, that's valid Hoon expression. Why does it blow up here?
Because the standard library is not included in that. There's no add.
Right. I've done this extremely constrained scope picture, and I actually don't have my standard library. I don't have any access to that value, even though it exists in my current scope. So if I were to do add, assuming A existed, that would be how I set it. So what that means then is if I want to run this together, let me see, I'm going to run a slop of, in this case I'll do my current scope, which is dot equals 5. Okay. And so now what I've done is I've carried out a new operation. So slap says take an AST and evaluate it against a subject, a vase, right? A type information with value. Slop is saying take 2 vases and merge them into each other. By convention, I actually did this backwards compared to the way we would normally want to think of it, which is I would want to put the current operating context in the tail. This is because the search path It's a depth-first search from left to right, which means that new information needs to go at the head as you compose this. Otherwise, you're going to be looking at old information as you work through this. So there's a little bit to, we call this the Vase algebra, but it's essentially the process of either combining bits of information that you have so for instance, one way that this essentially gets used in the compiler is as you add new information, new expressions to what's going on, you are slopping these values into your current picture of the execution environment. And then when you've added the information to the execution environment and you're ready to query it for information, you slap that vase and you get the information back out of it. So ignore the names, but you can see conceptually what's going on there and how that is a compiler-like operation to produce that. They're not actually that complicated as code artifacts. So you can see, so slop here simply says, dangerous word in a talk here. What it does is it says, take the head of both and put them together, and take the tail of both and put them together, and then label it cell. We saw cell already, so what this is simply saying is it says, take the two types, put them together as a pair, take the two values, put them together as a pair, label the whole thing as a cell, you have a new type. Conceptually straightforward to do. Slap is a little more complex to look at here because of this mint information. Essentially what this is saying is create a new picture of what the code you're going to be running and then run it in 2 steps here. I promised you wouldn't actually need to read Hoon to understand what's going on, which is why I demonstrated everything before I looked at any of this code here. Now, this is Hoon. We're going to talk through it. You don't need to know anything because there's comments on the right, and we'll talk about what those comments mean. The thing that I've elided up to this point, to a large extent, is what do we mean when we actually talk about type? I showed you an atom and I showed you a cell, but while that sort of describes what Nock is, it's missing a lot of the dynamic executable pieces and so forth that you'd like to have, both in a compiler and in a living execution environment where you actually want to run code. So type in Urbit means one of these many things here. What you are primarily interested in is the little things that start with the %. And so what that means is that several of these are only used in the compiler. They don't result in final code. But what this does is it gives us a system for talking about atoms, right? So we talked about those raw values there. It gives us a place to talk about pairs. Let me see. I actually had some nice terminology to break this out that it would be a shame to simply ignore and leave to the sands of time here. Okay. Yeah, so noun means that we have an undiscriminated noun, which means we have a value, and for whatever reason, we haven't decided or had to decide whether or not it's an atom or a cell or some other kind of thing. We have a void, which, to my understanding, is kind of a placeholder inside of the compiler. We use this information inside the compiler, and we use it in the final result, but you don't always see the same things in both because it's an intermediate step. A core, this is Urbit's conception of an object. It's a Nock construction that has a particular layout. To plug the workshop a little bit, we're gonna look at what that layout is and how you would use it actively, but that's what it does. A face, which is, here we called it a namespace, but it's like that label, right? When I said A equals 5 and I attached that value to it, that information was then carried around in the type. And so a namespace simply means that at some level you have attached a label to a collection of subsequent nouns. And so when you refer to something in a search path, what it is looking for is a namespace inside of a namespace inside of a namespace all the way down through the search path until it finds the thing that you want as the particular value there. A fork is a type union here, so we said union, but it's a type union. It means that it could still be one of several kinds of things. A hint is an annotation, which is it's a note to the runtime. Basically, you can kind of think of this as being like a C pragma. For instance, you're sending information to your compiler or your runtime to behave in a certain way, but you have to keep track of it because it is part of the Nock code. It's actually not executed in the same sense as the rest of the code. It's a label. It's telling it information about what's going on. And then a hold is interesting because it's a deferred type. And what that means is that, for instance, if I have a list of information, I know what the first value is in this list when I evaluate the list, but then there's still a hold sitting after it for the rest of the list. And so there's kind of this interesting cascade of information as you step down to find out what's going on there. Actually, let's briefly look at, yes, okay. Let's briefly look at what an example of that would be, because there's an interesting consequence of this. Okay, so a list, in Lisp, an S expression is a list. It's this first-class thing. In Hoon and Nock, we're going to say that a list is a null-terminated tuple. Kind of analogous to C, right? Like C, a character array is this sequence of bytes, and you end it with a /0. So it's a similar kind of concept there. We're going to write it something like this. And the type that it generates from me writing this null-terminated value, you'll notice that the value resolves to 1, 2, 3, 4, 5, 0. I have this nice syntax where I can put a tilde in front of my square brackets there, and it gives me this value. But what it resolves to actually is it recognizes this as a 5-tuple with a tail. It doesn't say this is a list. Structurally, it's a list, which is interesting, but it doesn't say that it's type-wise, it's not a list. So type-wise, I might say something like golf15, which would give me the values 1 to 5 inclusive as integers. And it gives me a different type value here. It gives it to me as what it calls here an iterator, right? It just means that it can go forward there, but structurally, it's the same value. There's different type information associated with it. And so if you're working with certain list operations in Hoon, for instance, some of them need to know that it is a list because they're going to treat it in such a recursive way that they have to know it's a list. Some of them don't care, and so if you hand them something that is a null-terminated 5-tuple or something like that, they don't care. They'll process it the same way because they're working on the data in a certain format. And so you get different discriminations that go on in your operating platform as a result of type decisions that are made as you work through this. Now let's look at. All right, we looked at slop, which was how we throw two of them together. We looked at slap. Here's kind of an interesting piece. This is one of the pieces that we're going to use. We're going to use slab. This is one of the things we use when we are asking information. Let's see, I wrote that. I think it only needs the type, which, yes, okay. So a slab is a way of looking into a type, which in this case is the head of the vase. I only need the head of the vase. I don't need the values in it. And telling me whether or not a given name exists. So it's only doing a search for things that match the namespace type, and then telling me if one of those exists. And you can imagine this is useful when you're trying to do something like an eval without crashing, because you would like to know whether or not you can actually do this, right? Does the face exist in my type before I start trying to run this code and actually see a crash? And so the metacircular interpreter and other things actually use this. Let's see, there's slam, which is a way of running a function, given a function and its argument is vases, produce a vase containing the result. That's a moderately interesting one. Text is a really interesting one. Okay, so if you think about writing a pretty printer for functional programming language, you need to have information. So you're handed a value, and you would like to display this information in the way that is most appropriate for the value. And you've all seen systems that don't do this. It used to be kind of fun on the web circa like 2000 when you might mistype something and you'd get this really funny message dump of error codes that weren't interpreted the right way or values that weren't interpreted the right way. Kind of related to the data validation problem, although that's more of an input than an output thing. But here what we're saying is, we're handed a value, we want to print this value the right way. If it's a hexadecimal value, we want to have a 0x in front of it. If it's a binary value, we want to have a 0b. If it's a cell, we want to make sure that we're putting square brackets between the two values and a space, and they both have their own types. Those don't have to be the same types. If it's text, we don't want to dump the hexadecimal equivalent of the ASCII. Or worse, we don't want to dump the unsigned decimal equivalent of the hexadecimal of the ASCII. We want to dump the ASCII. We want to show the ASCII. And so this Vase mode operation stuff also turns up in your pretty printer as a result of that. And so there's a function called test. And what it will do is accept an input and then turn it into kind of the most parsimonious, given the information it has, what's the most parsimonious way of representing this vase, this value, or this type value pair. And so here, for instance, I gave it that null-terminated tuple vision of what's going on. And so it wrote this as a 1, 2, 3 sig, 1, 2, 3 empty value. If I were to do it with Golf instead, now it picks up differently, and its default way of displaying a list is to put the sig in front, and so we get this. Now, there are some mismatches in the system where, the way that you would write it naturally as a null-terminated tuple actually turns out to be the output. So it's not a completely circular picture of what's going on here, but you can see how those do relate to each other. Now let's see, we've got some bits and pieces on raw Nock. I'm not going to worry about those. Let's see. We've talked about type. We've talked about Vase algebra. We looked at the Lisp example. Probably the other thing that's worth comparing to here, let's see. Here we go. Okay, besides Lisp, any Haskellers in the room? Okay, what's dynamic? All right, so dynamic is kind of a similar way in some sense of carrying this information. It lets you pack values of different types into a uniform container, carry around, manipulate if you want to that container, and then at runtime, you can actually run those values, those data types that you put into that container against the things that it thinks it has and let it run or crash or whatever it needs to do at that point. Although in Haskell, I think it produces like a none or something. Haskell doesn't have a none. Haskell has a nothing in Haskell. But it's a very similar sort of thing. In Hoon, because of the evil Vase stuff, you are and should get a runtime crash. If it's metacircular, it won't take down your system, but it will give you like that, Hoon value not found or whatever, if the types don't match. Probably the other thing is that makes it feel different from Haskell, but makes it feel more Lispy, is that because the Hoon vases are kind of closer to the metal, because they can trivially result in Nock code, and because you can very directly manipulate them as a noun object, you can insert values, you can alter values. They're mutable in this sense that you can mess with them. I think Vases end up feeling more like a dynamic interpreter, both at compile time and runtime than dynamic does there. All right. Phenomenally, although this quote has nothing to do with my talk, in this fashion I become a tree, I become a vase, you can pick up or drop at will. I actually found a quote from a poem about trees and vases that is not completely out of left field to talk about using vases to pick up and drop at will. So thank you, N. Sexton, for putting that together. Hoon used to actually expose a lot more of the affordances of this directly. The old build system called Ford would let you pull in values as what it called cages from disk, and then you could you had all these operators that would let you pass these around and make decisions on their basis and everything. And it was kind of a mess in many ways for the end developer to have to be concerned with this. Like you want a compiler, you want a build system that does all this stuff. You don't want a end user developer to have to do these manipulations when it's not kind of a boilerplate conventional thing to do. Anyway, all right. So yeah, so in conclusion, by having this kind of Vase algebra that lets you combine type subject information, this lets you do things like imports, library builds, REPLs, other things. Essentially, it gets you metaprogramming, validation, but still retaining that simple target ISA of, in this case, Nock, but other things for execution. So you can sort of think of it as like a gradual typing pipeline. As you move from this you want to have statically typed code. You want to have untyped Nock result. But in your compiler, you're going to have to do these manipulations that feel kind of dynamically typed, and then you're gradually typing all the way down until you actually lose type again at the bottom in a slightly ironic way. But this is what it's allowing you to do as you carry these around. We use this a lot when we're working inside of the kernel in Urbit and Knockapp and working on these systems. But I think there are lessons for thinking about this if you're building an interpreter or a REPL as well, about how you might use this kind of operation to produce your transpiled or your intermediate code target, AST, whatever you're doing on your way to finally resolving this. Thank you.